Hello, hello, hello. This is the screencast for the solutions to the Chapter 20 AP Physics 2 homework problems due on September 2nd. So I'll include a PDF as well, but I want to go through each of these a little bit. So problem 7 was saying you had 1 times 10 to the 12th, that's 1 trillion electrons added to charge A. A and B are touching each other. They're both conductors. They're the same size. So essentially, it's asking how many total charges are on each. So half the total, 5 times 10 to the 11th electrons, end up on each charge. I think they wanted to convert that to coulombs, so the conversion factor is 5 times 10 to the 11th electrons times 1 coulomb over 6.25 times 10 to the 18th electrons, or you can multiply this by the reciprocal, which is 1.6 times 10 to the negative 19th coulombs is the charge on 1 electron. Either way, units cancel out and you're left with coulombs, and that's the coulombs charge on each. Negative 8 times 10 to the negative 8th, or negative 80 nanocoulombs. For 14, you are asked to find the distance between charges. And I want to make sure that I'm looking this up right, so I'm going to take a second and open my book up. You can hear me shuffling the pages here. So for problem 14, a small plastic sphere with a charge of negative 5 nanocoulombs close to a sphere with negative 12 nanocoulombs. If you have a force, what's the distance between the two? So first of all, I'm going to convert everything into standard units. So essentially, we are given this charge. You should know the constant is 9 times 10 to the 9th. You're given the force. So we rearrange to solve for r squared. R squared is 0.000, I think is 659, maybe. And then take the square root of that, and it's 0.0257 meters or 2.57 centimeters. I'd leave it in meters. So that's the distance between those two. Problem 24 is asking you, has a bumblebee. Oh, I thought this was really cool, actually. The bumblebees can detect electric fields. So it's been sensitive to an electric field of 60 newtons per coulomb. Could a bumblebee use this to detect the presence of another nearby bumblebee if that one has a charge of 24 picocoulombs? Well, if you look on your handy-dandy AP formula sheet, you'll find that the prefix pico means 10 to the negative 12th. So that is a charge of 24 times 10 to the negative 12th, which is 2.4 times 10 to the negative 11th coulombs. We're going to assume it's a point charge. We're going to use equation E3. So rearrange again to solve this distance. And we get 0.06 meters or 6 centimeters. So, yeah, that's reasonable. That's like, I don't know, a little less than 3 inches. And on a B scale, that's pretty good. Problem 29 is a vector problem. You're given a picture where you have 2 charges here, and you're asked to figure out the electric field at this location. I think the key concept of this, the big idea, is that if you look at these, since they're both positive, the field points away from both of them. In that case, that means that due to the symmetry of this point being midway, well, along the line of what's midway between the 2 charges, you find out that the vertical components of field cancel out, but the horizontal components, which would point to the right, add up. So essentially, if I can find out the electric field of one interaction, either this top one or this bottom one, then I can use vectors and trigonometry to figure out the net field. So first of all, I had to figure out that distance. Well, use Pythagorean Theorem, 5 centimeters on each side. The overall distance here is 7.1 centimeters. Well, that's 0.071 meters. This is our formula E3. Which is right here. And plug in the numbers for that, because it said these were each 1 nanocoulomb, and I end up getting the electric field is 1,785 newtons per coulomb. So that's the field at this point caused by this charge. Now I'm going to have to do my thinking. I did the calculations, I got to do the thinking. Essentially, the vertical part, like I said, cancels out, so only the horizontal parts add up. So if I draw a triangle down here, this component is what I'm interested in. Well, since it's going to be a 45, 45, 90 triangle, I want to find this horizontal side. That's the cosine of 45 degrees, although obviously for a 45-degree angle, sine or cosine give you the same amount. So I take this overall field, find the horizontal component is 1260 newtons per coulomb to the right. That's the field at this point caused by this. This field, or the field at this point caused by this, is also going to cause 1260 newtons per coulomb to the right. Those will add up. The vertical components of the field will cancel out. So taking a look at that, we have a net field of 2520 newtons per coulomb to the right. Problem 33 is asking about a capacitor, and it's asking about the electric charge on each plate. So this is the formula we've had for that. I'm trying to see if this is on your formula sheet. I'm pretty sure it is. I think it's formula E9. I should write that down. And so we've got the electric field. We're trying to find the charge on one plate. This E sub 0 is vacuum permittivity. That is 8.85 times 10 to the negative 12. That is on your formula sheet also. And we need to not use just the side length, but the area of the capacitor squared. So 4 centimeters or 0.04 meters squared is 0.0016 square meters. Rearranging, solving for Q, we find that each plate has 14 nanocoulombs, or 1.4 times 10 to the negative 8th coulombs. I think 35 was the toughest problem of them all for this. So what you've got is you've got two capacitors, plates, and they're circular. It says they're 12 centimeter in diameter. Well, I know I'm going to have to do something with the area of that. Annoying thing is 12 centimeters diameter becomes 0.06 meter radius. I'm going to use pi r squared to find the area of those circles. The area of each one is 1.13 times 10 to the negative 2 square meters. So part A is asking which plate, the upper or the lower, is positively charged. If you have a bead that's a mass of 1 gram, a charge of negative 60 nanocoulombs, and it's suspended halfway between these. So if you notice I drew this picture, this is actually, pretty important. Because it lets me know that gravity would be acting down, and the electric force would have to be acting upward. So if the bead is negatively charged, and negatives repel negatives, and negatives attract positives, that means the bottom plate has got to be negative, the top plate has got to be positive. That will cause an electric force upward. And to be in equilibrium, these two must be equal to each other. Well, I can figure out this gravitational force down by using m times g. The mass, though, we got to put in kilograms. That's 0.001 kilograms. And I used 9.8 newtons per kilogram. You could also use 10 newtons per kilogram. So anyhow, that's the force of that. I use my formula E2 here. Essentially, and I rearrange it to solve for the electric force, although I could know that that electric force, again, is the same as what I got over here. And I use it actually to rearrange to solve for the field strength. So I get that the field strength is 1.63 million newtons per coulomb. So that's the field strength between here. Now you might think I'm done, but I'm using this field strength back with this formula, which is E9, to figure out the charge on each plate. So this charge Q, negative 60 nanocoulombs, is the charge of the bead, not the charge on the plates. So now I'm going to go ahead and use this again. See if I can drag that over. I don't know if I can drag that over. I don't think it's going to let me do that. Wouldn't that be nice if it did? Nope. So I'll get rid of that. But this again is formula E9. And we get that the charge on each plate is 1.63 times 10 to the negative 7th coulombs. Did some algebraic rearrangement, or 0.16 nanocoulombs. 37 should have been pretty straightforward, I think. It's kind of a neat model of a cloud and like a mountain or something like that. The charges build up where it's close, so that electric field is stronger close. Really, the area should be much closer here and then get less and less and less. I don't think I showed that very well. Finally, for 51, 51 was saying you had two equally charged 1 gram spheres placed 2 centimeters between their centers. So when released, Each begins to accelerate at 225 meters per second squared. What's the magnitude of the charge? So I start with my master law of all physics, Newton's second law. We know the acceleration. We know the mass of each of these is 1 times 10 to the negative third kilograms. So I can figure out the net force. And that would be an electric force. So now I'm going to use that net force that I found with Newton's second law, plug it over here into my Coulomb's law formula, and solve and get the charge Q. Because the charges are equal, Q times Q is Q squared. So I get that that would be 1 times 10 to the negative 14th Coulomb squared is Q squared. Q, I take the square root of that, 1 times 10 to the negative 7th Coulombs. So this problem actually ignored gravitational attraction, but if you look at it, this force is 0.225 newtons. I used the formula, which I learned in first year physics, or you might have learned in first year physics, figured out the mass of each of these, plugged it into the universal gravitation formula, same distance away, and I got 1.67 times 10 to the negative 13th newtons. So in other words, this is ridiculously small compared to the electric force, and therefore we can ignore it. It'll cause negligible effects. So hopefully that's okay. That's a lot of talking.